having, just the issues of science is our next speaker, Dr. Ian McCausland. I know has been active with the NPA many years ago, but hasn't actually come here to join us for a long time. It's a great thrill and pleasure to have you here. He just wrote a new book in the last year, which is in the back. I hope you pick up a copy. Dr. McCausland worked personally with Herbert Dingle, and if any of you don't know who Herbert Dingle is, you better find out, because he was one of the people who actually wrote books on relativity in as early as the 1930s, am I right? I'm not sure. Real early, and he was the world's authority on Einsteinian relativity at an early date, and sometime later came to challenge Einstein's ideas, and wrote numerous papers on it, and got ostracized for his efforts. He did write a book called Science in the Crossroads in 1972, and it was about that time that you came in contact with him, I think. And so he kept up a correspondence and has been writing about issues of relativity for decades. So I'd like you to please welcome Dr. Ian McCausland.
Thank you very much, Greg. It's a pleasure to be here. And as Greg indicated, this is essentially about my collaboration with Professor Herbert Dingle. This is Professor Dingle. He was a very eminent British scientist. I think you can judge his eminence by the fact that this picture comes from the archives of the British National Portrait Gallery in London. This is the book Science at the Crossroads, and it was published in 1972, so I'm celebrating the 40th anniversary of that, and it's the 40th anniversary of essentially my collaboration with him. He was essentially the first critic of the orthodox result of the clock paradox, or the twin paradox. I'm sure you're all familiar with it. The twin paradox says that an astronaut going away into space and coming back years later would be younger than his twin brother who had stayed at home. He then he disagreed with that result. He said that they should age equally. Then later he came to the conclusion that both results arrived from the special theory, and that therefore the special theory contained a contradiction. In my book, A Scientific Adventure, I described how he had written about this. And I also came to share his view that the special theory contained a contradiction, and my book is my book deals with that. I should perhaps explain this peculiar picture on the cover. This is a left-hand side is a print by Moritz Escher, a Dutch artist, and it's a very strange space. One of the strangest things is, these two little men here are walking from left to right along the same staircase, but one is walking upstairs and one is walking downstairs. That's relativity for you. If you wish to look in YouTube under the heading of Escher Relativity, you can find an animated version of this in which the little men walk about. Okay, so the central question in my book is there or is there not an internal inconsistency in Einstein's theory as described in his original paper? And the answer that I emphasize as described in his original paper on the subject, because the answer is then contained in this book, which is a collection of papers on relativity, in English translation, of course. And I go rather beyond Dingle in this, because Dingle argued that experimental support for the theory depended on circular arguments. I say experimental support for the theory is completely irrelevant. If you think that's extreme, suppose a scientist wrote out a theory today and showed it to a colleague, and the colleague said, read it over and said, there is a logical contradiction on page 6. Suppose the scientist said, without even looking at page 6, I will prove to you by experiment that there is no logical contradiction. Well, I think his colleague would laugh at him. I cannot exactly show that there's a logical contradiction on page 6, but here's something that shows somewhat of a problem in the theory. This is one paragraph taken from this translation, and I split it into two parts because that's the way I did in some of the papers that I wrote. And the underlined part on the left-hand side is essentially the statement of the clock paradox, the orthodox result. If we have two clocks, one of them goes around in a circle relative to the other, then it is the one that moved is slow relative to the one that stayed behind. I think almost every relativist would defend this with the utmost tenacity. But when you look at the right-hand statement, a balanced clock at the equator must go more slowly than a precisely similar clock at one of the poles under otherwise identical conditions. They're not nearly so sure of their ground. Excuse me, I'm going to take a break. The footnote says not a pendulum clock, but this is physically a system to which the Earth belongs. That shows that he's talking about a real result and not just a matter of observation. Now, Dingle asked the question about that particular result. He said, applied to this example, what entitled Einstein to conclude from his theory that the equatorial and not the polar clock work more slowly? Here's one answer. There are three answers from Dingle, reviews of Dingle's book. He says the relative motion is non-uniform, therefore he says Einstein was wrong. Although he doesn't admit defeat. He says the prediction is not invalid because he was anticipating his later theory. Now, I hold the view that any answer to Dingle's question that's a valid answer must have the property that it would have been a valid answer if the question had been asked right after the paper was published. So if you imagine somebody being asked, or if you imagine Einstein being asked right after the paper was published, how do you justify this statement? Supposing he'd said, well, I'm not quite sure, but I'm working on a new theory, and so come back and ask me the question in 10 years' time, and I'll give you your answer. This is Whitrow's answer. I don't want to spend time in dealing with it because there's a lot that could be said about it, but the main point I want to make is that he is obviously supporting Einstein's view that the clock at the equator is working slower than the other one. Here is Maddox's answer, which says that Einstein was confused, or was confusing, and he says one clock is in a reference frame, the other clock's in a different reference frame, whereas Whitrow's answer, the previous one said that one is in a reference frame and, or associated with a reference frame and the other cannot. So there's all these three different answers. I made up an argument from the statement about the polar and equatorial clocks, and I essentially took a step back in Einstein's argument where he was talking about a polygon instead of a circle. And I imagined clock A at the center of a square and clock B going round the square at a uniform speed. Now, all observers will agree that clock B loses a certain amount of time in each transit around the square. Therefore, by symmetry, it will lose a certain amount of time in each going along each side. Therefore, it must be actually working slower than clock A in exactly the same sense as the equatorial clock compared with the polar clock. And then I suppose a clock C, which is traveling uniform speed through space forever in such a way that it is alongside clock B for part of its path, therefore it also must be working absolutely slower than clock A. But by principle of relativity, clock A could equally well be said to be moving in clock C stationary, so clock A could equally well be said to be moving slower than clock C. I published this as a paper called An Inconsistency in Special Relativity, and this was the start of my debate with Professor Jack Good. And I call this Good's answer because essentially it could be another answer yet to the question about the polar and equatorial clocks. He said about that statement, in any case, Einstein's statement was at least a slip in exposition. I call it Einstein's slip. And then on the same page of the same paper, he said Einstein's slip, when taken literally, immediately contradicts the kinematics of the special theory of relativity. He says all the inconsistency claimed by me resided in the slip and none of it resided in the special relativity. In other words, Einstein made a slip, so you can't use it. It's just an error. You can't use that as an argument against the theory. And then from the from the abstract of his last paper in the debate in 2006, what I previously called Einstein's slip wasn't a slip after all. And then after some other words, he said, this correction doesn't imply an inconsistency in the special relativity, although it would appear to do so to those who regard time travel as logically impossible. So he had conceded that it was not a slip, but he did not concede that it was still a contradiction. So this is the way his last paper left it. It was rather unsatisfactory. But I think it is fair to say that he failed to refute my argument. He died shortly after that at the age of 92, and but one of the things that came up in my debate with him was the properties of an inconsistent theory, and I can just deal with this quite briefly. Using well-known symbols of symbolic logic, P dot Q means P and Q. P dot Q is true if and only if P and Q are both true. P or Q is true if P is true, or Q is true, or if they're both true. Not P is the negation of P. So supposing we have a theory T with two postulates, like special relativity, postulates P and Q, whatever they are, to show that they're not consistent with one another, I say not P dot Q, which means they cannot both be true, they could both be false. But from the postulates themselves, we can deduce that P dot Q, and therefore we have a contradiction. So we use this disjunctive syllogism which says P dot Q or S is some new statement, doesn't matter what it is. We know that P dot Q is true, therefore we know that combined statement is true. But not P dot Q, therefore S follows. S can be any statement I wish. Could be the Earth is flat. I have not proved the Earth is flat. I've shown that from a theory having an inconsistency, you can deduce that the Earth is flat. You can also deduce any statement of the form, if you do experiment X, you can get result Y. So that means that a theory that has an inconsistency can match any experimental result, whatever. So from that I say it is completely illogical and untenable for any scientist to claim by experimental results that there is not an inconsistency. If there was an inconsistency, all the experimental results could be made to follow. Okay, there's another argument of Dingell's that I present as an appendix in my book, and I'd like to discuss it briefly. First of all, look at this is how Einstein showed that a moving clock runs slow, and this is copied from his book, Einstein and Infeld, The Evolution of Physics. The three pictures represent three instants of time. There's a stationary set of synchronized clocks. There's a moving clock. As you can see, as time goes on from step to step, the moving clock is further and further behind the stationary clock. Therefore, it is running slower. Dingle proposed an argument that said you don't need to use, let me just wait for a moment and then. Dingle said you don't need to use synchronized clocks. You can tell the time of any event by one clock at the origin of the system. Now, for example, imagine that I see something like a solar flare on the sun or some flash of light or something happen on the sun. I want to know when it happened on the sun. I look at my watch, I subtract 8 minutes because that's the time it took for the light to reach me from the sun. That's the same as saying that if there was a clock on the sun, or let us say beside the sun, that we could read from the earth, the reading I would see on that clock is synchronized with my clock according to Einstein's definition of synchronization. The time I would see on that clock right now is 8 minutes behind my own clock. So I don't need the clock. I don't need a synchronized clock up there in the sky to tell me what time that happened. So Dingle used I cannot expect to convince you in speech of the truth of his argument, but it's a long verbal argument of about 1,200 words in which it's very closely argued, and it says that if you measure the time intervals between two arbitrary events according to one clock in each of two reference frames, then the result should be the same no matter what pair of events you choose. Now, as I say, I cannot convince you of that here now. It's in the appendix of my book. I've given what I think is a reasonable summary of it in my paper for the conference. But Dingle showed that this was Dingle's equation to show that the time ratio of the two rates depended, according to the Lorentz transformation, on the events chosen. He started from the Lorentz transformation I've shown at the top. From that, he replaced t prime by delta t prime and delta x by delta x and so on. Then he divided through by delta t. So the left-hand side is the ratio of the two clock rates. The right-hand side includes a term delta x over delta t, where delta x and delta t are the space and time intervals between two arbitrary events. So obviously, according to the Lorentz transformation, the time ratio is dependent on the events chosen. So he says that according to his argument, his long argument is based entirely on Einstein's definition of synchronization. It does not involve any other theory of any kind. So by that he showed that the Lorentz transformation, he said, could not show the correct ratio of the two times. Good published a review of Tom Phipps's book, Old Physics for New. Tom Phipps's book had exactly the same argument of Dingle's in the appendix of his book as I did in the appendix of mine. And so Good wrote a review of that book, and he chose to try to refute Dingle's argument. So I've put the equation up there again that comes from Dingle's argument, and this is what Good said. But actually, both sides of the equation are equal to 1 minus v squared of c squared to the half, which is 1 over the quantity gamma, which appears in the there. So he says that's whatever the value of v in whatever events we choose, assuming we're referring to a pair of clocks, which one is velocity v relative to the other. Now he got that result by just plugging in v for delta x over delta t in the first equation. So he was he misinterpreted Dingell's equation essentially, so he failed to refute Dingell's argument. So what I'm saying is that Professor Good twice failed to refute arguments involving that are critical of special relativity. Now, I don't want to give you the impression that Professor Good was some kind of second-rate scientist. In fact, I think he deserves the highest praise for criticizing the Dingell's arguments and my argument, because comparing him to the relativists who hide behind all those illogical arguments and call the rest of us who dispute these inconsistent arguments, they call us crackpots or whatever. So I think I would like to pay tribute to Professor Good, who was also a very distinguished British scientist. He, I wish he and Dingell, I wish he had decided to criticize Dingell's argument while Dingell was still alive, and because that would have made a very remarkable debate if he had done so. He spent the last 40 years of his life as a professor at Virginia Tech, and he was a very distinguished scientist. His distinction may be assessed by the fact that this picture is from his obituary notice in the London Times. So considering that he had spent the last 40 years of his life in the United States, I think it shows he was a very highly respected person. As far as I'm concerned, I am proud to have worked with both these people.